No? Somebody was asking me about recording stuff. Anyway, whatever. Oh, I don't have homework 9 up there yet, but that's okay. Yes, I do. Homework 8. Okay. So, write a tic-tac-toe program. The program is smart enough to take advantage of 2 of its own marks in a row and to block 2 of its opponent's marks in a row. And if neither is possible, to make any legal move. This is going to be a human versus computer game. So the human will move the mouse around and click on the grid, and the computer will look at the grid and decide what the next move it should make is. I'm not asking you to work on the AI part of this at all. In fact, I'm discouraging that. So you go through and you just work on the interface and get it to follow these conditions up here in the first paragraph. Next week we'll talk about game trees and alpha beta pruning, and then it should be a fairly straightforward, not super straightforward, but it'll be a week-long assignment for you to add the AI to the tic-tac-toe game. And then with that AI, if you've done it correctly, the AI will play to a draw against a player that makes no mistakes and will beat a player that does make a mistake. No, that's a real phrase for game tree analysis, as opposed like a metaphor for.
It's kind of fun to see like prune trees.
Well, yeah, I mean you find that in graph theory all the time. They use tree analogies, and so the pruning is not an accident. You're right. Game trees tend to be really large. In fact, the tic-tac-toe game tree is small enough where you don't have to do any kind of pruning. You can represent the entire game tree fairly comfortably in a modern computer. What is it, 9 factorial possible game configurations, grid configurations? 9 factorials on the order of like 300, 400,000. So you can easily hold every tic-tac-toe board in memory and analyze it completely. And in fact, you will do that. You'll write a version of the AI that doesn't use any alpha beta pruning, and in fact represents the entire game tree in memory and plays the game following just the full game tree. But that's a luxury that you usually don't have in real game theory. And so I'm also going to ask you to implement a version that works on alpha beta pruning, which lets you analyze the tree to a certain depth, but then leaves off the rest. Every really interesting game out there has a game tree that is too big to hold in memory. Checkers, chess, Go, any 2-player perfect game that's interesting is impossible to represent fully in memory. So first things first, we have to. I'm restricting you to writing your GUI in processing, and processing is an open source development environment that runs on Windows, Mac, and Linux. You can go to processing.org, go to the download link, and choose your particular binary. Windows users, most of you are probably 64-bit, so just try the 64-bit. You'll find out really quickly if you're a 32-bit machine because the 64-bit installer won't run. There's Linux, there's Mac OS 10. Please do try to install this tonight and come to me with any problems. We're working on a week-to-week schedule here now, and so I don't want you starting this program next Monday afternoon and not being able to install processing. Because I know you'll start it next Monday afternoon. Okay. The documentation is all online. And again, that's at the main site. You click on reference, and they're just almost the complete set of commands that are available to you. And then there are several tutorials that I would suggest you, if you have a chance, you should read early and play around with. The first two, getting started and overview, I would suggest. Actually, the first three. First four, first five. Yeah, it just goes on. They're not terribly difficult for people like you that have had a fair amount of programming experience. You should be able to get processing up and running, especially with what I'm going to talk about today and Wednesday. You should be pretty comfortable with it in short order. So please do note those tutorials, and I think I've placed links to the main page. Yeah, so there's a link to the main page here and to the tutorials page here. Not sure why I put that on the 19th, but whatever. And then I have a little video here that shows you how to put your sketch on the web. I wrote one this morning. Let's see, math. That just does little bubbles, randomly generated bubbles that float to the top and disappear. So I wrote a little video that shows you how to take your processing sketch and put it on your MathLab webpage. And I'm using my MathLab webpage here, not Caret. So math.whitman.edu/tilde, your user ID, and then / whatever folder you've put your sketch in. And if you look at the video here, it will give you details on how to use that MathLab webpage.
So we don't actually have a page. We just have a domain that we can.
Right. That you can put stuff into.
Yeah.
Exactly. Okay. Processing. Let's go here. Let me just double check something for a sec here. So the stuff that I do in class today, I'm going to put in the examples directory of the class web page. So you've installed processing, you click, you fire it up. There are some preferences that you can set. You don't normally have to do this, but if you're wondering where your sketches are living on your disk, you should go to File, Preferences, and they're sitting in your sketchbook location. Inside that sketchbook location are the .pde files, the processing source files that you will upload to me for grading.
You can also just save them anywhere.
Yeah, but so yeah, if they're not in the right place, they're hard to run. So it's best to just leave them in the processing sketchbook directory, and we can talk about how to run it in other places. So I'm going to change my sketchbook location to the examples subdirectory of the class web page just for convenience, and hit OK. And now let me, what am I going to do today? I'm just going to talk about some basic, the basic overall structure of a processing sketch, and then what I hope to do is start building a tic-tac-toe board. So I'm going to start doing your homework for you. Mostly as a way of introducing you to processing ideas like color and coordinates and that sort of thing. I'm going to leave out some of the more mundane stuff, the stuff that I think you're well prepared to think about already, and that is like analyzing the board and deciding how to make a move to block 2 in a row, or how to make a move to win the game, how to check the board for a win. There are no easy formulas for that. You just kind of write a little function that will look at the current board and decide what the next move should be. Not really smart AI, just blocking 2 in a row or winning if you have 2 in a row. That's the extent of it, and otherwise just random placement in the grid of 9. So the rest of it, I'm going to leave that to you to think about, and the rest of it I'm going to use as sort of a vehicle for introducing you to processing. So let me save this guy, save as, or just save. And the naming conventions are a little bit annoying. I have to change my naming convention because the processing people don't like dashes in their file names, and they don't like file names that start with a number. So that totally wrecks my naming convention. So we're going to switch to April_22nd_2013, and I'm just going to call this, nope, no dashes, tic-tac-toe. So now I'm there, and if I go look in the sketch directory, I see that new folder is now created, and inside that is the .pde file. Processing Development Environment, I think, is what it stands for. That's the PDE file, and that's the thing that you would upload to me through the class upload script. And let me just remind you how that works. This is actually going to be a little bit less clunky than your normal upload. Because now it's actually going to function the way that it was intended to function. Not with links, but with a nice graphical user interface. I go here, 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 click on that guy, and I can't make any mistakes. I can't make any spelling errors. I click submit, and it's uploaded. So you don't have to transfer it over to the math lab and then upload it. You can just upload it directly from your computer. Yeah. No, I want your source also.
Okay.
Yeah.
That makes sense.
So the web page is there so that I don't have to load your sketch into processing every time. I can just click on the URL, I can look at it, see how it's working, and then I can have your sketch, your source code over here, and I can be typing comments over here in the source code and looking at it running over here.
So should we just comment the URL in the processing file?
Yes, in fact, I think I might have mentioned that, but I'm not sure on the assignment. But put the URL to your sketch in a comment at the top of your source code. I don't know if the font size is big enough here. Can you guys read that?
Yeah, that's all right.
It's okay. I can make it bigger. All right, let's talk a little bit about the main elements of processing. Processing, at least at the start, is really about learning what some of the built-in functions are. You're in the source code now, and just like in C++, where every running C++ program has a main, you're kind of already in main with this blank text editor. So main is already written for you, and you're kind of working inside of main. And then inside here are functions that you just write. The first reserved function is something called setup. It's a void function with no arguments, and the purpose of this guy is to initialize the variables and the size of the canvas and anything else that only happens once. Okay, and the other big one is the draw function. This is something, setup happens once, and draw happens over and over again. So draw happens many times a second at a rate that's set by frame rate. You don't have to set frame rate. By default, frame rate is just as fast as the computer can go. And that's usually sufficient. But if you have a really labor-intensive sketch, maybe you want to slow the frame rate down a little bit so that it's not really bogging down the computer. And if you do want to do that, you can go up here and just type frame rate in setup, because again, frame rate is something that would just happen once in a sketch. And you just tell it how many times per second you want it to happen. So that'll call the draw function 10 times per second. Another thing that happens in setup is the size of the canvas. And I'm going to start with a square canvas. And this is a 500 by 500 pixel canvas. The coordinate system is a little bit weird. Maybe not weird. For people that have done some graphical programming, it's perfectly normal for computational GUI programming environments. But for others of you that are sort of more math-oriented, it's a little bit odd. So I'm going to sketch here, talk briefly a little bit about what the coordinate system is. So in a processing sketch, once you declare the size, here's your canvas. And this is the width in pixels. That's always first. And in our sketch, it's going from 0 to 499. And then the height, again in pixels, goes from 0 to 499 in our sketch. And to access, say, this pixel right here, which is roughly in the middle, maybe you would put something like 250, 250. It's not perfectly in the middle, right? But it's close enough. Right, up to odd and evenness, 250 is near the middle. And this is the positive x direction. And what's weird is this is the positive y, which is opposite from what you learn in 8th grade algebra. Positive y goes down. Once you deal with that, once you get your mindset on that, it's not so bad. And everything is, all coordinates in processing are ordered, and they go x, y. So this is horizontal, and this is vertical. All coordinates in processing are horizontal first, and then vertical. And then the other thing is that positive y is down instead of up. Questions about that? So what's the coordinate of this pixel, the last one down there in the lower right corner? 499, 499. And the first one is 0, 0, and you can sort of guess the rest. You have to be careful, right? 500 by 500, how many pixels is that?
A lot.
It's a lot. Yeah. So keep that in mind when you're allocating these canvases. If you allocate a giant canvas, you're going to be correspondingly working your computer very hard. It grows like n squared, kind of. Yeah.
Doesn't processing also go on if you have a canvas relatively on your screen?
It'll like pop up the edge, I think, and sometimes it'll go to the back.
Yeah, you're probably safest keeping it in the screen, and certainly for our case, tic-tac-toe, 300, 400 at the best, at the most is what you need. If you do more exotic things with processing, yeah, you have to be aware of some of these quirky little things. Most people's screens are at least 1024 by 768 resolution, and in fact most people are higher. So if you keep your width less than 1024 and your height less than 768, you're probably safe. Any other questions about the coordinate system? Okay, once you get the coordinate system, idea in place, we can talk about putting some things on the canvas. Processing has a few built-in intrinsic shapes that it can draw.
Will it draw something off the screen?
Yes.
Okay.
So there aren't very many basic shapes that processing can do, but here's a list of them: arc, ellipse, line, point, quadrilateral, I guess, and rectangle, and triangle. Let's play around with, let's try line. I'll do one of my favorite doodles from when I was bored and sitting in your seat. Okay, so the line command. So we're in the processing reference page now, and it's telling me how to use line. You can probably guess how to use line. There are four values that you feed the line command. The first one are the x and y coordinates of the starting point of the line, and the second pair are the x and y coordinates of the end point of the line. And if you put that in the draw section, or in fact if you put it anywhere, it'll draw it on the canvas at that start and end. So let's do that. So we'll do line. Let's do one from the upper left to the lower right. Save it, run it, and there you have it. My favorite little doodle, let me see if I can sort of make a for loop for this. Control T will format for you. Let's see here. I want to go across the top. So let's do I times 50. That's across the top. Otherwise, keep it 0. And then I want to go down the left side. So let's keep that 0. And do this, make this 499 minus I times 50. I think that'll do it. Yeah. So here's a for loop that systematically draws us a sequence of 10 lines. Yay, Windows 8. Systematically draws a sequence of 10 lines, and you can see how this works. When I is equal to 0, let's look at just the starting points. This starting set of coordinates goes across the top of the screen. How do I know that? Because the y coordinate's always 0, and that corresponds to the top of the screen. Y coordinate equals 0. Remember, a positive y is in this direction.
Isn't the x coordinate 0 or I equals 0?
Yeah. And then for I equals 1, it's 50. I equals 2, it's 100. And so we're marching across the top in increments of 50 pixels. Okay? And then we march across, we march down the left side. So here, looks like I should have started it maybe at 1. Oops. Because that 1 on the edge there is not worth looking at. Grr. So the first one starts here at 50, 0, and it goes down to essentially 0, 450. And then those guys march up, and these guys march away, and you get this apparent hyperbola. That's a sort of a hyperbolic illusion. These are all straight lines, but the edge of this collection sort of looks like, in fact, very closely approximates a hyperbola. With this kind of systematic approach, you can draw very sophisticated geometric diagrams. What's really going on here is you're drawing this thing over and over and over again at 10 frames per second. Okay, let's talk a little bit about Yeah, let's talk a little bit about, yeah.
Could you, or I guess, I don't know, I guess two things. Every time it draws, does it refresh the screen and then redraw?
Yeah, let me show you, let me give you another example and show you how what's actually happening. It does not erase the screen by default every time through. And a good way to see that is to draw an ellipse and put the center of the ellipse at the x-coordinate of the mouse and put and the y-coordinate of the mouse, and then give it a fixed radius, let's say 10. Actually, this is the width, so it'll be a radius of 5. So I'm going to draw a circle centered at the mouse coordinates, mouse x, mouse y, with radius 5. So right now there's nothing there except an attempt to draw the circle. You can see it there tucked up in the upper left-hand corner, and that's probably just because the mouse x and mouse y start out at 0. But as soon as I move the mouse into the window, it's only 10.
Unbelievable.
I think it's kind of more interesting at a low frame rate than if I crank it up. But I can crank it up. Let me comment out the frame rate command.
Does it actually just go as fast as it can then?
As near as I can tell. Oh, is that what it is? Okay. So we could try cranking it up. I mean, it should be able to handle this because it's such a simple program. So let's try 60. Oh, it's still commented, yes, thank you. Not going to change anything. I don't know if that's changing or not. Let's crank it up even more. That's still pretty cool. I like that. You can get rid of this behavior by setting the background every time in the draw command. So there's a background function. And we'll just set it to, say, 128. I'll talk about why that's 128 in a second. And now they're being drawn, but they're being erased at a very rapid rate. So you get that effect. One circle. And when I stop, it's still drawing the ellipse. It's just the ellipse isn't moving. But it's doing it over and over again. Let's talk a little bit about that 128. Some of you may be familiar with how colors work in most graphical programming environments, others not. Essentially what you do is you have 3 channels: the red channel, the green channel, and the blue channel, RGB. And this is an additive color model where, for example, if you set all 3 channels to maximum, then you get white, and if you set all 3 channels to minimum, you get black. So it's an additive color model. That's in contrast to sort of, if anybody dabbles in painting here, oil paints or what have you, mixing paints is what's called a subtractive color model. And if you sort of, in an additive color model, if you mix RG and B, you get gray, and if you really increase the intensity, you get white. But in a subtractive color model, if you mix red, green, and blue, you just get gunk, just garbage. So it's a different model. It's the model that essentially describes light. It's what Newton did when he put the prism in front of his window, and the sunlight shines in and it hits the prism, and then it disperses into the rainbow. That's an additive color model. And we see white when we see essentially equal mixtures of the whole spectrum. That's additive. So color and processing is a mixture of these 3 channels. And you say, well, wait a minute, Schiller, you only put one number in there, 128. What's going on there? Well, we're also taking advantage of overloading, function overloading here. If any place where you can specify RGB, if you just use one number, like I've done here, then the default is grayscale. So one number essentially sets RG and B all three equal to that same number. And that gives you a grayscale. And if you stick in 0, you'll get a black background. And if you stick in 255, which is the maximum, you'll get a white background. So there's 0, there's the black background, there's the circle. And then the maximum is 255. That'll give me a white background, there's the circle. Jamie?
Two things.
Yes?
If you put in like red and green, but forget the blue, does it default the blue to something or freak out?
It's a good question. I think it'll just freak out.
Okay. And then how do you change the color of the ellipse?
Yeah, let's talk. We'll talk about this too. Let's experiment with Jamie's question though. So 255, 255, R and G to 255, B we forgot to set. I'm hoping for a compiler error. Nope.
Good old Java.
No, I have another guess. You'd have to know something. Yeah, I think it might be alpha. So all combinations, it looks like 1, 2, 3, and 4 are all going to mean something. And people that heard the word alpha, don't worry, I'll talk about it in a minute. But I can actually add two additional arguments. All red, so red is on full, green is totally off, blue is totally off. The background should be red. And it's an additive color model, so if I turn on full red and full green, there's no reason really that you should know what this is going to be, but does anybody know? Yeah. Get yellow.
Why don't we use primary colors for this? It's always confusing.
You know, I am not an expert here. Go ahead.
That's the primary colors, however you want.
Subtractive are different color models. Subtractive color models.
Maybe that's it. Maybe in
For a stupider reason, it's easier to make LEDs in red, green, and blue, and that's what they've used for the screens.
But the thing is, this color model predates LED displays by many decades.
CRT's same deal, though. They have red, blue, and green guns. This is how they
I
work.
think the human eye has like red. I mean, it's a little more complicated than this, but to some level, it has red, green, and blue colors. So, like, the range of colors that we can see can be very well approximated by defining a certain amount of red, a certain amount of green, a certain amount of blue. And you can also combine other primary colors like CYMK for a printer to get the same range of colors, but red, green, and blue are direct.
Yeah, and I think I would not discount Ben's explanation either about additive versus subtractive color models. The primary colors that you learn in art class are usually in the context of painting. And so it may be that, which is a subtractive color model, and might suggest, what is it, red, yellow, and blue?
Yeah, I think it has to do with probably what elements we can get.
I think you're absolutely right.
Colors that
Yeah.
look like.
Back in the Renaissance, possibly even before that, blue is a really hard pigment to get a hold of. And in fact, the Catholic Church would actually specify what you had to use to make blue pigment during the medieval times and all that. And that's where the word sacred blue or sacre bleu comes from, is, you know, the shawl that you put around Mary or whatever in your oil painting had to use the sacre bleu, and it was a particular kind of pigment. Okay, let's go back to less liberal artsy kinds of discussions. And what were we gonna do? I forgot already. Really? Let's do fill and stroke, and then we'll talk about alpha. So. This is how you set colors. What about colors on the shapes themselves? Let me go back to a more boring background. We'll go with white. What we can do is set the fill color, again according to these same rules. We can set the fill color to, say, red, and the stroke color, I don't know, let's make it blue. So stroke refers to the boundaries of figures, and fill refers to the interiors of figures. And that's for figures that have boundaries and interiors. If you're drawing a line, then you're only using the stroke. You're not using the fill. I should make it bigger, shouldn't I?
So you think it's purple instead of red?
Dope. Control Z. There we go. Yeah, what were we going to do?
You have it as purple instead of
How do I make purple?
0 in the first, or you made blue by 0 in the first one.
Yeah, we can do blue. Okay, so there you see an example of fill and stroke. You can thicken up the stroke with something called stroke weight. And this is really just pixel width, roughly speaking, so I'll make the stroke 3 pixels wide instead of 1 pixel wide. And I can see a substantially thicker boundary on that.
Which way would that sort of thicken towards?
I think it goes from the center out, you know, so.
Could you just give us an error message? Just a little like,
Sure. So it'll pop up down here.
Way less helpful than C++.
yeah, I think if you take through like 3
I've been using it a lot the last several weeks, and I find the error message is pretty informative, but, you know, what do I know?
A null pointer or something like that.
Yeah.
It's just a disaster.
like exception.
Well, that's the thing. That's Evan's getting to one of the big differences between processing and C++, and that is declaring variables. Processing separates the process of declaring a variable and allocating the memory to that variable, and it's something that you have to get used to. It's a Java thing. It's a Java thing because processing is really Java.
You also don't have to, or you don't have to specify what kind of function links are either, do you?
You mean like
Void or anything.
you have to do void, but you don't have to do protected and
Yeah. If you want a return type, you need to give it a return type, and if you want arguments, you need to give it an argument, and that stuff's pretty similar.
You don't need to declare them though. Definition and declaration.
Right. It's there's no prototype at the top and then definitions at the bottom. You just write the function. Okay, let's talk a little bit about alpha, and then we'll move on. So let me keep the stroke weight at 3 just to keep it interesting, and let me draw a fixed, let's make a rectangle, and we'll make the rectangle. For rectangles, what you do is you specify the upper left corner and then the width and the height of the rectangle. So I'm going to put the upper left hand corner, let's say at 100, no, let's say 200, 200, and then let's make it 100 wide and 100 tall, and let's give it a slightly different color. In fact, I'll just give it default. Well, yeah. Yeah, let me move this guy above. So if I want to give it a different color, essentially I just reissue the fill and stroke commands. So we'll do fill, I don't know, 0, 255, 0, so that'll make it green. And let's make no stroke, just for the heck of it. So if you don't want any stroke, you do no stroke. You could also set stroke weight to 0. Then we draw the rectangle, and then we do fill and stroke again, and stroke weight. And the way that processing works is whatever the most recent fill command color was, that's what the next shape is going to get. Whatever the most recent stroke color was, that's what the next stroke is going to get. And so this draw command running so quickly is changing colors, drawing, changing colors, drawing over and over and over again. Okay, I told you I would talk about alpha. Alpha controls the transparency or the opacity of the object, and we'll just do it with the fill color. So you can always define a color with 3 variables, R, G, and B, but there's an optional 4th color that tells you how much you can see through it. And it's also from 0 to 255. And for 0, you are maximally transparent or invisible. And for 255, you're maximally opaque or not transparent. So let's put it sort of right in the middle, 128. And I'm actually going to make a note of this up here. The 4th argument is called alpha, and it controls the transparency of the color. 0 is fully transparent, and that'll be invisible. And 255 is fully opaque.
I like to think of alpha as opacity rather than transparency.
Yeah. So let's run this guy. There's our green square in the middle. There's our red-filled circle with a blue boundary. You'll notice the red is not quite as red as it was before. That's because the white is shining through from beneath. And as I move over, I get to see things underneath in a really striking and interesting way. Questions about that?
Does the order in which you draw something determine its layering?
It does. So by drawing the rectangle first during the draw sequence, it goes underneath the circle or the ellipse. Order matters. Okay, let's talk a little bit about tic-tac-toe in the waning 3 minutes of the class here. I'll stick with a 500 by 500. You know what? No, I'm not. I'm going to introduce one more concept that's quite useful in processing, and that is the notion of a global variable. So let's put that up here. There's sometimes there are variables that you would like to have scope in several different functions. You would like to be active in several different functions. For example, perhaps you want this. Well, yeah. This isn't really one of them, but let's do it anyway. Int width x and width height. Yeah. Sort of an unnaturally named.
It is the global variable.
Oh, I know. And so is width. And yeah. I think that's just a bad example of a global. Let me hit a global when it's actually useful. Okay. So let's make the canvas. Oh, I know what I'll do. Int canvas x and canvas y, say. And then you declare the variable up here, but sort of by processing tradition, you shouldn't initialize them up there. You should initialize them in setup. And then we can use those variables here to get the same effect that we were getting before. All right, let's start talking about drawing a tic-tac-toe board. So, if you want to draw a tic-tac-toe board, that's 2 vertical lines and 2 horizontal lines, strategically spaced. So let's go with a white background and let's go with black grid. So we'll do a line, and we can go say the top of the first vertical line should be at canvas x divided by 3 and 0, and then the bottom should be at canvas x divided by 3 and canvas y, say. And once we get that guy, we can do the others. Where's the next one, the next vertical line? 2 times that. And then 2 times that. And that should be good for the 2 vertical lines. Let's do the 2 horizontal lines. Okay, the horizontal lines, we want, we're always starting at the left end, which is x equals 0, and then we go down y over 3, and then we go to the right end, and then we go down y over 3. And in fact, I'm just going to copy that guy. And change those to 2.
Do you need the star, or does Java also assume that any number next to a variable is multiplication?
I don't know.
You need the star.
Don't you need to start in C++?
Yeah.
Definitely. Yeah. Okay, so there's a simple tic-tac-toe grid. Maybe you want to change the weight on that a little bit. So stroke weight, maybe 3 or something, and you get the idea. Okay, what we're going to do next time is we'll continue to develop this tic-tac-toe board. There are a few things that we have to do here. We have to think about the human side of it, right? How are we going to represent the game board at any particular point in time? How are we going to tell where the human clicked? You know, if they click here, or they click here, or they click here. We'll talk about a lot of that stuff next time. And we'll also talk about a really efficient way of drawing the markers, the X and the O. Yay, Windows 8. And we'll learn a little bit about the transforms that you can do in processing, translation, rotation. If you learn how to use those, they seem really daunting at first, but they can really save you a lot of time and effort. So we'll talk a little bit about that. Until then.